Hello everybody, back again to talk about some of the properties of the equilibrium constant with emphasis on the math. First thing is here's an example. I'm just going to stick with the aqueous phase. Well, we could actually use this for aqueous and gas phase Kc. It's applicable to both for solutions and gases. When you have it written with partial pressures, that's solely applicable to gas phase. So here the input's molarity, we have a reaction. Let's just for the sake of argument say everything is in solution. And every property I talk about here is wholly applicable to K sub P as well. Here's a reaction, everything is in solution, so it can all go into the equilibrium constant. I just want to say before we move on, is equilibrium constants have a wide range of values. They'll always be positive, greater than 0, but they can range from tiny numbers like 10 to the minus 34. For example, here's a really small one, the autoionization of water from H2O to H plus to the hydroxide ion OH minus at room temperature is 10 to the minus 14. That's a relatively small number. And we'll also see equilibriums that are very large numbers like 10 to the 5, 10 to the 6. And the interpretation of that is that when you have a really big number, like 10 to the 6, is that you have a lot of products at equilibrium relative to reactants. You might end up with only a trace amount of the reactants in equilibrium with a whole lot of the products. If it's the converse case, if it's a tiny number, if K is tiny, that will indicate that the reactants are huge relative to the products that are small. And then you have other numbers that are in the order of, medium-sized numbers like 1, 5, 10, and so forth, where that means they're about in the ballpark of each other in terms of composition. We'll be able to put numbers on all this, but it's good to have a feel that if you see something with, like, for example, autoionization of water, where you have a tiny number, where you realize that there's not a lot of H plus and OH minus floating around relative to the water itself, or if you have a process where there's a big number at the end, like 10 to the 4, 10 to the 5, 10 to the 6, then it means it goes almost to completion, but there's a little bit residual of the reactant species in equilibrium with the products when you get there. So these are good gut feeling type of things to have when you look at it, when we start to do the math of this, to know if you're, for example, doing something wrong. Also, just to have a good interpretation of physical processes that are relevant for whatever you go on to study, where equilibrium comes into play. And I guarantee if you go on in chemistry, for sure, biology, biochemistry, cell biology, subjects like that, that equilibrium will be an important part of it, along with kinetics. And so here's the general form. Again, products over reactants for an arbitrary reaction. Let's just take it, for example, everything's in the aqueous phase. We've decided, in this case, we will have to use molarities as the input, regardless of what the exponents are here. We report the end answer dimensionless. That's a convention, we'll take it. And so that's great. Products over reactants raised to the exponents are the stoichiometric coefficients. And so let's say we were to flip the reaction around. And this often comes into play when we're doing math associated with combining things together. We might flip a reaction around, or we might want to take a reaction system that's reversible is a matter of perspective, what you call the reactants and the products. So you could write this reaction around, because there's a forward weight and a reverse rate. You could just switch the whole thing around and change about how you think about it. In that case, C and D are the reactants and A and B are the products. And so I'm going to just call the new equilibrium constant for that Kc prime. And in that case, it's just, it's products over reactants, but it's the inverse of Kc. So one of the baseline rules is that if you invert a reversible reaction, the resulting equilibrium constant is just the inverse, K to the minus 1, or 1 over, this is Kc technically, 1 over Kc. It's the same thing for Kc prime. And I'm just using primes and double primes, what have you, as a way of denoting a different equilibrium constant numerically for some sort of process that we've done to a reaction. And let me just say, for this to hold, I'm assuming they're at the same temperature when I do these observations. the equilibrium constant, whatever it is, Kc, Kp, what have you, is a temperature dependent function. It's a temperature dependent function. Let's take another process. Let's say, for example, we have A, species A with a coefficient A in equilibrium with B, with the coefficient B of this balanced reaction. We could write a Kc for that reaction. It's going to be products and overreactants raised to their respective coefficients. And let's do similar for C and D, similar format, products over reactants. When we add these together, I did want to make it a little different than above. We have, in this case, A plus C with their coefficients equals, as the reactants with the products B and D with their coefficients. When you do this, what you'll notice is you get products over reactants, same form, and that's simply the product of Kc and what I'm calling Kc prime for the second reaction. We call this reaction 1 or reaction 2. We could put a 1 or 2 subscript if you want to do that. I just call this prime. So the product of these two is going to give you Kc double prime, which is for the reaction added together. Meaning when you add reactions together at the same temperature, you multiply their equilibrium constants together to give you a new equilibrium constant. That's an important property. Here's another property that kind of ties in with this. Let's keep the master reaction right here. So we have, let me erase a little bit here. I'm using a sock for an eraser now. I was talking to Chat, and Chat says, do not use paper towels, that you will scratch your board. And I don't want to buy another board for the money and also the delay time. I'm making these videos. I'm trying to make as many as I can for you all. They're not perfect, but I think they're good to explain the ideas. Always read the descriptions. If I do make a small mistake, I'm not going to record over the video. When I catch the mistake and I rewatch it, I put something about it in the description section. These are not I'm not trying to make glossy videos. I'm making good videos to learn by that are similar to my lecture structures. And just like in lectures, when I misspeak, I correct it, or I put something online. I'll put these any errata in the description. The content overall solid. So let's say we were to multiply by n. Just n is a number, not equal to 0. It could be any 1, 2, 3, what have you. Let's say we're trying to come up with some other description of the reaction. We're trying to combine reactions together, and we need to multiply through so we can add together in such a way that things cancel. That could be a reason why we multiply through by a factor. So we'll multiply through by a factor of n. So we have NA A plus NB B going to n lowercase c to c plus n times the lowercase d d. Same form, products and reactants as the original one. So when we write, I'll just call it again Kc prime. Let's look at this. We could write A to the NA. Oh, I'm going the wrong way. Products, excuse me. So, real easy to do. We'll go C to the NC, D to the ND, little lowercase d, A and A, B and B. And we could factor like this. We could write this as C to the C, D to the D, A to the A, B to the B. And this is all raised to the N. And that's the same thing as saying this here is Kc. So we got Kc on the inside raised to the n, and I'll just write it like Kc to the n. And so that's another form. So if you want, and we could call that, if we want, Kc prime. And so that's another thing. If you multiply through an equilibrium system. And I should say this all applies if you're doing similar operations like this with Q's. We're just tending to work more with K's for the actual operations, but you could do this with the reaction quotients as well. These operations are generic. So if you go through and you have Kc, and let's say this was, let's say for Kc was a number, let's say just for the sake of argument it was 2, and so let's say we multiplied through with n is equal to 3, just for some reason or another, but this would be 2 raised to the 3 power, or 2 times 2 times 2 is 8, right? So that's all it is. It's as simple as that. You just take your original rate constant and you raise it to the power of whatever you multiplied through by. So when you go through on pages 7, 8 into 9, I believe, there's some problems dealing with this, and quite a few. And so you have some where you actually work through combining together, and not all the numbers are simple like 2s and 3s. Sometimes you have Kc values on the order of really small numbers or big numbers, so you get used to doing it. And so that's a good set of operations. I'm going to leave the video now. If you're working along in the notes and the skill builders, go work the problems that are roughly on page 7 to 10 in the note set, work through them. You can check your answers in the worked out note sets. Do not just look at the worked out note sets and go, cool, I got it. It does not work like that. And then go to skill builders. There's some more problems in there. They might even be redundant or similar problems, but rework them anyway, and then check your answers. A really bad habit is to just, doing nothing is the worst, but second to that is just looking at my solutions going, check, I got it, without actually working the problems. That is a major trap, and it's one of the reasons I'm hesitant about putting solutions online, but I gear the course to people who are really trying, and people who are really trying will be working the problems and using it just like a solution guide if you purchase one, which is nothing wrong with it, but it can be misused. So that's a tidbit of advice that I'm giving you on this to do well in this course. So hopefully this is works out for you. You should work these problems because you'll be using these type of operations quite a bit. They should be just like baseline skills. You shouldn't have to memorize these, just get used to doing it. Next time what we'll talk about is how to interconvert between, if you have Kp and Kc for gas phase reactions, how you can write them in terms of each other arithmetically. I'll go through a little proof with that, and that's a very useful tool for exams and for future reference. So on that note, have a good day, and I'm out. Take care.